All right, welcome back. We are looking at Unit 6 for Math 160. We're moving into the standard normal distribution. Now, you're probably thinking, what do you mean? We already saw this. You're right, we did. We drew a bunch of normal curves and we labeled the horizontal axis from -3 to +3. And then we drew dotted lines and we shaded certain regions and then we used the empirical rule. That's all fine and dandy. We also use the z-score formula. That's great too, but we're actually going to dive much deeper into this particular section, which actually includes using a z-score table to provide even more accurate information about the percentage of the population that falls within a certain range. So you'll see this in just a little bit. We're going to do a quick recap of the empirical rule to make sure we're on the same page. If I move too quickly through that, let me know, okay? But let's scope it out. All right, chapter 6, normal probability distributions. All right, let's start off with introduction. Donna, would you read A, B, C, and D for all of us, please?
Yeah, sure. There are infinitely many normal probability distributions. B, they are all related to the standard normal distribution. C, the standard normal distribution is the normal distribution of the standard variable Z called the z-score or the standard score.
Perfect.
D, the z-score or the standard score is the position a particular value of X has relative to the mean measured in standard deviations.
Perfection. Thank you so much. It's always nice hearing another voice, you know, it's just, I love it. Those things that I highlighted are incredibly important. The standard normal distribution, we're looking at the z-score, the standard score. So we're taking values and we're standardizing them. It allows us to compare apples to oranges, really, literally. And then the meaning of the z-score or the standard score, that's really important to think about, right? It's a position of a particular value that it has relative to the mean. So you're looking at that raw data score and you're giving it a z-score, a standardized score, and that gives you a particular position, okay? Properties of the standard normal distribution. So recall this empirical rule. We've seen this already. We played around with this. Notice that your horizontal axis here has all of these tick marks, -3, -2, -1, 0, 1, 2, 3. These values and everything in between and everything outside of them, they all represent your standard score. Those are your z-scores. They also represent the number of standard deviations you are from the mean, right? So like, just as a reminder, if your raw data value has a score of 1.0, right, a z-score of 1.0, that implies that we are one standard deviation above the mean, or we have a z-score of 1, right? It's just a reminder of this dialogue that we had a bunch of classes ago. Abby, no worries. Please keep us posted. I hope that everything is okay. that I don't like the way that message landed. If you, for instance, are looking at a z-score of -2.0, that means you are 2 standard deviations below the mean, right? With the mean being here at 0. Also, we talked about the percentages of the population within certain boundaries, within, you know, 1 standard deviation below, and the mean that's 34% of the population, things like that. So we had all of this dialogue already. We're going to continue and expand on this idea. Stephanie, would you read B and C?
Sure.
Thank you.
The total areas under the standard normal curve is equal to 1 because the total area under the standard normal curve also called the density curve, is equal to 1. There is a correspondence between area and probability.
You pause right there. That's really, really, really important. When we talk about the area under the curve, that's the same as talking about the likelihood. And we know the likelihood of any event, if we think about all of those outcomes for that event, then the total probability is 1, right? We know this, we've seen this many, many times, especially when we were talking about probability. Keep going, Stephanie, one more.
The distribution is mounted and systematic, or
Symmetric.
yes, symmetric, sorry.
It's okay.
Extends infinitely in both directions, approaching but never touching the horizontal axis.
That's an interesting piece too. So even though these tails look like maybe eventually they'll touch the horizontal axis, they actually never do. So it's basically stating that regardless of where you are, your probability is never going to be 0 exactly. And it's never going to be 1 exactly, but we are going to get very, very, very close. Lainey, awesome. Glad to hear it. Good. Actually, Stephanie, do one more.
Okay. The distribution has a mean of 0 and a standard deviation of 1.
Yes, think of the standard deviations as taking steps. 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean. That's essentially what we're referring to. Your mean is going to be here at 0. Whatever your raw data value is, that's going to represent your mean, and that position will be here at 0. The mean for a sample is X bar. The mean for a population is going to be mu. Okay, keep those values in mind. I don't know what my computer is doing right now. All right, how about, let's go with Sam. Would you read E and F?
Okay. The mean divides the area in half by 0.5 on each side. This means 50% of the area lies to the left of the mean, and 50% of the data lies to the right of the mean.
Yes.
Okay. And then F, nearly all the area is between z equals -3 and z equals +3. The empirical rule is a fairly crude measuring device that enables us to find probabilities associated with a whole number, not multiples of the standard deviation, within 1, 2, or 3 standard deviations of the mean.
Perfect. The empirical rule is limited. That's essentially what that's saying. It's a crude measuring device. So we have these estimates here, right? It tells us that between -1 and 0, the z-scores of -1 and 0, 34% of the population will fall within this bound. That's great. But what if we wanted to know the percent of population that fell within -0.8 and 0? Now we're limited. Now we're like, wait a second, how do I know for certain what that value is? That's what I meant by, we are going to consider this as kind of like a backup to what we will be doing in this class, which is using the z-score table. Starin, yes, you actually want to make sure that for your population parameters, that mu does not have any notation around it. So mu alone would be the mean for the population. X bar is going to be the notation for the mean of a sample. Okay, so be very careful with those two things. Perfect. Very nice. Let's turn the page. Angelica, would you read part 3, finding areas under the standard normal curve for various z-scores? So go ahead and read A and B.
So A is to use the z-score chart to determine the area to the left of the z-score. And then B is percentage, proportion, and probability are basically the same concepts. One, percentage, 50%, is usually used when talking about a proportion, about half of a population. And two is probability. It's usually used when talking about the chance that the next individual item will possess a certain property. And then the third is the area is the graphic representation of all three when we draw a picture to illustrate the situation.
That is so important. The Z-score chart gives you the area to the left. And then when we talk about percentage, proportion, and probability, we're essentially referencing the same concepts, right? We know that the percentage, 50%, is half of a population. That's proportion. We know that probability refers to chance. There's a 50% chance, right? There's a 0.5 chance that something happens. And then area, physically, area is the graphic representation. So we are looking at the shaded region. So that's essentially what's happening here. Okay, we are going to find and shade the area under the standard normal curve given the following conditions. So all we're doing is shading. We're going to find it and then we will shade it. Okay, so let's take a look at the curve. And you're welcome. I have inputted all of the curves for you so that you don't have to draw every single one every single time. We want to find the area to the left of a z-score of negative 1.32. So the first thing we're going to do is we're actually going to plot the point negative 1.32, which is probably about here. And we're going to draw a dotted line up. We can label that point negative 1.32 just so that we have this. And we want the area to the left. So you can use a different color, you can use your pen, you can use your pencil, you can use a marker, whatever you'd like to use. I'm going to use my highlighter to fill in the shaded region. So we simply just shade in that region. Out of curiosity, if you had to guess, what percentage do you think falls in that region? If we had to guess.
25.
Yeah, like something small, right? Something pretty small. So we're going to actually figure that out exactly. So we're looking for the area, not percentage, although we can turn it into a percentage. If you take a look at the notes that you printed out, guess what? Look at the very last page. It's like a gift, right? It's like, ooh, there's a gift here. So we have a very last page that has all of your z-scores. For whatever reason, we have two separate tables. One has 4 places after the decimal. The other has 5. It really doesn't matter. It's all about an estimation anyways. 4 places is just as good as 5. Really, really, I'm like being totally honest with you. So don't freak out that we have a different table on the back. It's not a big deal. So here's how we read the z-score table. Our z-score is a negative 1.32. The great thing about the table that we were given is that these values already represent the area to the left of the z-score. So we're looking for negative 1.32. Check it out. So we start here and we go down to negative 1.3. Negative 1.3 is about here. And then we want our hundredths place to be 2. So do you see the column headers? This would be negative 1.30. This would be negative 1.31. This would be negative 1.32. So we actually want the intersection between negative 1.3 and 0.02. So ones and tenths place, and here's my hundredths place. We go to where they intersect, and we see that we have the value, and maybe I'll just highlight that. We have the value 0.09342. So that represents the area to the left of that z-score of negative 1.32. We knew it was going to be very small. So keep this table handy because we're going to use this a lot. Are there any questions as to how I found negative 1.32, that z-score?
Yes. Sorry.
No, that's okay. Let's do another one. Let's
So how
see
did,
what-
my question is, how did you get to 0.02? Like, do you know what I mean?
I do. Let me give you another example. What if I want you to find the area to the left of a z-score of negative 2.85, right? So
Can
this
you
is
bring
a-
it down a little bit? Because I
Yeah.
can't see, right?
Yeah, so let's say we want this z-score.
Uh-huh.
You're gonna start off by seeing, do you notice that these first values right here are in this vertical column?
Yes.
So we're gonna go to negative 2.8. Do you agree that the hundredths place is the 5? So we're gonna go to where the 5 is.
Yes, but how did you get to 5?
You just read the number. So negative 2.85, that 5 tells us which column to use. Yeah, it's just finishing the z-score number. So negative 2.85. This would be negative 2.86. This would be negative 2.87. Does that make more sense?
Okay, okay, I see now.
Yes, beautiful. Okay, perfect. Very, very nice. And all of the values in the table represent the area to the left of the z-score. All of these values are to the left. So we find that the area to the left of a z-score of negative 1.32 is 0.09342. This has an area equal to 0.09342. So we have found the area. We can say that the probability that a value falls within this range is 0.09342. We could say there is a 9.342% chance that a value falls in this range. So there's many ways to describe this, okay? But that's essentially what we are looking for. Let's do it again. Let's find the area to the left of a z-score of negative 1.75. So same thing. We're going to plot that point, negative 1.75. That's approximately here. We're going to draw the dotted line up. We want the area to the left. So let's go ahead and shade that region in. Again, it may be helpful to label that as negative 1.75, just so that we know that's the value we're looking at. So we want the probability that our value falls within this range. Take a look at your z-score table, and I would like you to look up the z-score negative 1.75. Excellent. Once you have it, yes, awesome. Lucy, you're like, boom, done. 0.04006. Ava, same thing. Excellent. That's exactly right. Yes. 0.04006. So the area is equal to 0.04006. Let me double check that. We want to be really, really careful how we copy this down. So yes, 0.04006. Let me just show you. Negative 1.75, that's here. And there we have it. So just be really, really careful with how you copy that down. Good. Turn the page when you are ready. On your own, please answer parts C and D. To the left of a z-score of 1.49 and to the left of a z-score of 2.24. Just take a couple minutes to do this. Beautiful. For a z-score of 1.49, we're approximately here. We're going to draw our dotted line up, 1.49. We're going to shade the region to the left. The really great thing is, as you're doing this, I kind of want you to think about the percentage that you should expect. Like, this is pretty massive. We know that from 0 onward to the left is 50%. We know that another standard deviation gives another 34%. So far we're at 84%. So we're probably between 84 and like 90, 92, maybe even more than that. So when we take a look at our z-score table, 1.49, 1.49 is here, we find we're at about 93%. So we were pretty close in terms of estimations. So an area of 0.9319. What I'm going to write here is additional notation for you. The probability that your z-score will be less than 1.49 is 0.9319. So area and probability mean the same thing. We know that the area is 0.9319. The probability that this happens is 0.9319. Okay, I want to make that connection at this point so that you can feel comfortable with this idea. To the left of a z-score of 2.24, we're approximately here at 2.24, and we want to shade everything to the left. Okay, when you look up 2.24 on your table, you find that this has an area of 0.9875. So we can write out that the probability that our z-score is less than 2.24 is going to be equal to 0.9875. Perfect. So area and probability mean the same. I have a question for you all. Let's look at part C, because I think C is much easier to see for right now. If you know that the area to the left of the z-score is 0.9319, without using the table, how can you figure out the area to the right?
You subtract it by 1 or
Done.
subtract the number from 1.
Perfection. Did you hear Angelica? She's like, duh. The entire area under the curve is 1 because total probability is 1. So if you think about that, where the entire area under the curve is 1, well, what would be left over? If I told you that this is 93% of the population, you would be like, well, here's the other 7, right? You would easily be like, yeah, this is what's left over. So to figure out the area to the right, and I'm just going to put a note, to figure out the area to the right, we subtract the area to the left from 1. So we would do, in this case, 1 minus 0.9319. If you punch this into your calculator, you'll find that the area to the right is 0.0681. And that's going to be something that's interesting for us to remember. This area here to the right is 0.0681. Okay, something to keep in mind. We knew if we had 93% to the left, we'd have approximately 7% to the right. So because we have 93.19% to the left, we have 6.81% to the right. Excellent. Any questions for me on this concept so far? Score, Starin, yes, I see your answer. Very, very nice. Beautiful. And in which case, Starin, would you read notes 1 and 2?
Probabilities associated with positive z-values are greater than 0.5000 because probability includes the entire left half of the standard normal curve. Make it a habit to write the z-score with 2 decimal places and the areas probability percentages with 4 decimal places.
Beautiful. Thank you so much. Surujni, would you finish this off? Note 3.
Sure. To find the area under the standard normal curve between any two z-scores, you will subtract the smaller area from the larger area.
Wait a second, hold that thought. That's something we have not discussed yet. And I don't know why I stuttered here. So let's get rid of this. That was a stutter. If you want to find the area between any two z-scores, you subtract the smaller area from the larger area, which is a very interesting concept. Keep going, Surajini. We're going to see this in a second.
This applies even if you have positive or negative z-scores because the areas are what you will be focused on. Find the area to the left of each score, then subtract them to find the area between the z-scores.
Yes. Look at how nice that is. We essentially have a formula provided to us. Find the area to the left of each score and then subtract them to find the area between the z-scores. If you were ever wondering, it's right here, literally typed up for you. This is a process you're going to take. Let me prove that to you. Go ahead and turn the page. Let's look at practice problem number 2. Find and shade the area under the standard normal curve given the following conditions. So we want to find the area between a z-score of negative 1.65 and a z-score of positive 1.65. Look at the notation here for probability. That's very, very interesting, something to keep in mind. So let's go ahead and plot negative 1.65. That's approximately here. We're going to draw our dotted line up. And we're going to plot the point 1.65. That's approximately here. And we're going to draw the dotted line up. Perfect. We want to find the area between these two scores. We're going to shade this particular region. There it is. And now let's use our z-score table. Anthony, what is the area to the left of a z-score of negative 1.65?
Point zero. What? Where? I lost it.
I know I did.
0.04947.
Yes, 0.04947. Here is the area to the left. It's as if we shaded this region, even though we don't want this region, but that's the area. Okay, so we're looking at the area to the left of negative 1.65. Good. Thank you so much, Anthony. Kelly, what is the area to the left of a z-score of 1.65 positive?
Hold, please. I dropped my binder.
That's okay. That is okay. I'm looking at mine too. Everybody should be looking at theirs as well to figure out what that area is.
.9505.
Yes, 0.9505. And now we learn to figure out just the area between. Think of these as distances, right? Wouldn't you subtract them to get what's just in between, what's left over? So if you take this much away from your total, you're just going to be left with what's in between. So we are going to subtract the area. So we've got 0.9505 minus 0.04947. So let's punch this into our calculators. 5 minus 0.04947. And what are you all getting for yours? Are you getting 0.90103? Thank you, Sam. 0.90103. So we can state that the probability that we fall within this range is 0.90103. It's a nice way of writing that statement, okay? You simply subtract those areas. I wanted to show you this visual so that you could feel confident with the fact that we really do need to subtract to find the area between. Any questions for me so far? Another thing to keep in mind is that we took the larger number and we subtracted the smaller. Area cannot be negative. Probability cannot be negative. So you want to make sure that you're always taking the larger number and subtracting the smaller. Okay, hearing no questions, why don't you all try part
Can
B?
you please go up a little bit?
Yeah, for sure. What's going on? Talk to me, Donna.
Oh, no, nothing.
Oh, you were writing like the statement. Beautiful. I'm going to pause the video and give you an opportunity to try part B. Beautiful. So we are going to plot our points, 2.03. That's approximately here. It's like practically on 2. And 3.13. So it's approximately here, which means we're shading this tiny little tail, right? We can already guess that that percentage, that probability is probably going to be really, really, really small. When you look up the area to the left of a z-score of 2.03, again, I could just kind of write out here what that looks like. So when you use your table for 2.03, you get a probability of 0.9788. So 0.9788. When you look up to the left of 3.13, we get 0.9991. And then remember, take the larger one and subtract the smaller value. Always, you want area to be positive. When all is said and done, you should get 0.0203. Yes, thank you, Emma. That's perfect. You can put a 0 in front if your heart desires. Let's write out the actual statement. The probability that our z-score will fall within this range is going to be 0.0203. Very, very nice. Any questions for me on this so far? I feel like this is going great. Cool. All right, hearing none, let's look at part C. And we may as well do this together because this is kind of wrapping up this idea. So let's plot the point -2.35. So we'll label that -2.35 and -1.50. That's approximately here. And you want to shade just between those two values. Notice that you didn't have to be told between, you know, just by looking at the inequality that we are referencing the area between these two z-scores. All right, would someone tell me what is the area to the left of -2.35? Yes, Emma, thank you, 0.00939. I'm just gonna turn the page so that I can write this, okay. 0.00939. What about to the left of -1.50? Yes, Mike, perfect. Mike typed into the chat 0.06681. Clearly the larger one is 0.06681. Let's go ahead and subtract these two. So we're going to say that the probability that our z-score falls within this range is equal to, go ahead and share the results in the chat with everyone if you would like, or out loud. I'm typing this into my calculator too. Emma, perfect. 0.05742. Excellent. You can write your probabilities 0.0574. Recall that we had a note related to the number of values after the decimal for a z-score. That should be 2. And then the number of values for your area or probability, that would be 4. But because we had 5 values on our table, I am comfortable with being just a little bit more accurate. So don't be alarmed by that. When you look at your Lumen assignment, you may be provided with the opportunity to actually look at the table in Lumen itself. So I would use that table if it's provided to you. If it isn't, then it will most likely specify how many places to round to. As always, if there are any glitches that you notice within any of those assignments, please let me know right away, okay? So that I can correct that. Perfect. Let's move over to notes continued. We already discussed this. Angelica already revealed this piece to us. So notice it says, to find the area under the standard normal curve to the right of a z-score, which is going to be something that you should highlight. It is important to keep in mind that the area under the entire standard normal distribution curve is equal to 1. So you will subtract area to the left from 1. Just as a reminder, that's exactly what we're doing. You're going to subtract the area to the left from 1, and that'll give you the area to the right of a z-score. No big deal. I do want to show you another perspective, though. Okay, whenever you're ready. Find and shade the area under the normal curve given the following conditions. So you want to find the probability that z is greater than negative 1.48. First off, here that language greater than, that means we're shading to the right. So let's plot the point negative 1.48. That's approximately here. Draw your dotted line up. And this time we're going to shade everything to the right because z is greater than this value. Okay, this is really important to note. Z is greater than the value, which indicates shade to the right. Greater than indicates shade to the right. Okay, that's really important to keep in mind. Now, there's a couple ways to do this. You can go to your table, look up the area to the left, which is negative 1.48. When you have that, would you share that with the class? The area to the left is Sam, what'd you get? Nice. Mike, Kelly, they're both sharing in the chat. Yeah, Sam, what'd you get? You can share with everybody.
I got 0.06944.
Excellent. So we know the area to the right, the actual shaded region that we want, is going to be found by taking 1 minus 0.06944. Now I want to show you something really, really cool. Can you take your z-score table and flip it over? Can you look at the positive side? Look at 1.48 on the positive side. That reads 0.9306. Let's hold for a moment. I'm going to do 1 minus 0.06944. Interesting. When we looked at the positive side, 1.48, we saw the area to the left was 0.9306. Look at my calculator. 0.9306. What this is highlighting for all of you is the fact that our curve is symmetric. So a trick, if you wanted to use this, and by the way, let me just write out 0.93056, which is the same as 0.9306. You could simply look at the positive side. You can imagine that instead you plotted the 0.1.48 and you were looking at everything to the left, because that would have the exact same value of everything to the right. Isn't that kind of neat? It's because of the symmetry. If that throws you off, then just stick with this particular strategy. Find the area to the left, subtract from 1. But if you wanted the area to the right, all you have to do is look at the the opposite z-score, and that will always give you the area to the right. So look at 1.48, 0.9306. So we find it here. Okay, again, that's completely up to you. You don't need to use that perspective. Just something to think about. So let's write out our statement. The probability that the z-score is greater than negative 1.48 is 0.930. You can write 6 or you can write 5, 6. It's completely up to you, however accurate you'd like to be. What questions do you have for me? Okay, hearing none, let's do one more. On your own, I'll give you a couple minutes to do this. All of those are looking fantastic. So 1.93 is approximately here. 1.93. We draw our dotted line up. Notice we want the probability to the right because it says z is greater than 1.93. So we're going to shade this region. I could do it one of two ways. I can find the area to the left first. So we use our positive side of our table. We look for 1.93, which is here. So that's 0.9732. That's to the left. 0.9732. So this side is 0.9732. The area to the right, which is what we're looking for, we can find by doing 1 minus 0.9732. The other thing we could have done is instead of looking to the left of 1.93, let's look to the left of negative 1.93. If I look at negative 1.93, I get 0.02680. I'm going to prove to you that that's exactly the area we were looking for. So when we take our 1 minus 0.9732, we get 0.0268, which is exactly what the other side of the table showed us. So that is a shortcut. Again, like I said, you don't have to use that if you don't want to. Let's go ahead and write out our statement. 0.0268. It's funny because when you all started to do this, I literally said, oh, I'm going to go to the negative 1.93 and I'm going to look at that area because that's my answer. I'm able to do this in a fraction of the time because of that concept, because of the symmetry under the curve. Good. Very nice. Any questions at all for me? Okay. Let's look at a
Actually,
couple
I
more.
have a question.
Yes, yes, awesome.
Okay, so when we looking, you know how it says like area to the right? So I thought we were actually like, okay, so as we shed to the right, I thought that we were looking the area to the right, like the one we get from the back.
Oh, great question.
Right here will be the right side, and then we look for the left side by subtracting 1, 2.
With these tables, Donna, it actually always gives you the area to the left of the z-score.
Okay.
Either side always gives you the area to the left of the z-score, right?
Okay.
That's what both of those sides give. So one of the things to think about is if you do want the area to the right, you could just do 1 minus whatever that area is. The shortcut that I provided is not necessary for you to use. So if that concept's just a little weird, you're just like, what the hell is she saying? I wouldn't even worry about that. I would focus on, let's find the area to the left using my table. And then to find the area to the right, simply do 1 minus that value. Okay. Good. Good, 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 good. All right, let's take a look. Finding the z-score associated with a percentile. Now, this is a little bit interesting because this time we're kind of going to work backwards. So check this out. We can also use the z-score table to find the associated z-score for a given percentile of a normal distribution. Think about it like this. If I ask you what is the percentage of values that fall in this range, you would say 2.68%. If I said to you, what is the percentage of values that fall in this range, you would say 93.056%, right? So that's how we can convert area to percentages. That's no big deal. let's go back to another diagram that we have. If I wanted the percentage to the left of the Z-score, this is 98.75%. So we know that the second we pass this halfway point, we're going to be greater than 50% of the area. So something to consider. So let's go to our current problem, which is we want to find the Z-score associated with the 85th percentile. What we mean here is that we want to shade 85% of the actual curve, right? But we're referring to 85% and below. When you think about visiting a doctor and saying, you know, let's say the doctor says, oh, your child is in the 90th percentile for height. What that means is your child is taller than 90% of the other children in this category for height, right? That's what it means by percentile. Think about your SATs. If you had to take an SAT or an ACT or PSAT, anything like that, typically you would get your results and they would describe your percentile. They would describe how you fare against everyone else who took that same assessment. So if you scored in the 73rd percentile, you outperformed 73% of the population. That's nothing to sneeze at, right? If you outperformed 73% of the population, that's a huge feat. So you'd be in the 73rd percentile. So think about that position, meaning you're going to be above the mean and you're shading everything to the left of that. Okay, let me show you. And this will probably be our last problem for the day. So find the Z-score that is associated with the 85th percentile. The first thing I'm going to do is I'm going to turn this into an area. So 85% will be turned into a decimal by simply moving that decimal 2 places to the left or dividing by 100. So that gives us 0.85. Now remember, area is typically represented as 4 values after the decimal. So we can write that as 0.8500. Next, we already know that the area to the left of 0 is only 50, but we want 85. So we know we're going to end up shading more than that. We might be somewhere between a Z-score of 1 and 2. With our knowledge, we know that this is 50%. From 0 to 1 is another 34%. So we definitely know we're going to be between the Z-scores of 1 and 2. So let's go to our table. What we're going to do now is we are going to look at the areas inside, and we are going to find 0.8500 or as close to it as possible. So we're going to look for an area of 0.8500. And notice what I find. And this is your table. You can write all over this if you want. 0.8500 sits right in between these two guys. Is it right in between both of these, or is it closer to one or the other? You tell me, is it closer to one or the other?
It's more closer to the other one.
Which
Like,
one?
So the 8 point
The
and
8508.
Yeah, I agree. 0.8500, we're closer to this guy. So guess what? We have found our Z-score. So what I'll do is I'm going to circle this number because we're closer to it. What is the Z-score associated with this number?
Would it be like 1.04?
Yes, that's exactly correct. Perfect. So we can answer and say that the Z-score is going to be equal to 1.04. So let's plot that. It's right about here. It's like super close to 1. We knew this. We were really expecting that to happen. And the area to the left is approximately 0.85. We know that specifically it's going to be 0.8508, but we're very close to this. So this is around 85%, approximately 85%. Again, we always want to choose the one we are closer to. So I'm going to make a note here, and this will conclude our class session for today. The area happened to be between two scores, 1.03 and 1.04. When we looked at that table for 1.03, we found that it had an area of 0.8485. 1.04 had an area of 0.8508. So when we think about the position of 0.8500, we are actually closer to this one. We are closer to 0.8508 than we are to 0.8485. That is why we choose the 1.04, because we're closer to that area than the other. Very, very, very nice. Excellent work, everyone. We flew through that. We did 7 pages today. That was phenomenal. We will continue with this idea on Wednesday. Excellent work, everyone.
Professor,
Yes.
I have a question. So you just say that the 0.85, the whatever the number what we just got, is a lot closer to 8508. So we chose 8508 for the answer.
Yes.
Yeah, but what if the number is like right in between?
If it's right in between, that's actually pretty atypical for that to happen. If it's right in between, then honestly, the software would allow you to choose either answer. If it's right exactly in between, chances are that that's not going to happen though. Chances are, even if it's 0.001 closer to one than the other, you'll have at least some sort of designation. So I wouldn't worry about that too much.
All
Excellent. Great question.
Thank you.
You're welcome. Bye, everyone.
Bye.
Sunny, stay
Thank
after
you.
class, okay?
Yeah.
Bye.
Bye.